In this video, I'm presenting a summary of the vector product. Sometimes the vector product is also called the cross product. Let's take a vector A in the Cartesian coordinate ax along the I direction plus ay along the j direction plus az along the k direction. And then let's grab also another vector B. B equals bxi plus byj plus bzk. And I want to find the cross product between A and B. The result of this cross product is a vector C that will have coordinate along the x, the y, and the z axis. I know that by the definition of the cross product, the magnitude of C is the product of magnitude of A times magnitude of B times the sine of the angle in between the two vectors. And to find this product, I really need just to multiply all the component of A times all the component of B. But this will be a long process, so I use a trick by building a matrix 3 by 3. This trick will help me if I calculate the determinant of this 3 by 3 matrix. It will help me to find out the coordinate of the vector C. On the first row of the matrix, I simply place the unit vectors I, j, and k. On the second row, I will place the ax, ay, and az. On the last row, I do have bx, by, and bz. And please remember that the sequence, which one goes on the second line and which one goes on the last line, on the last row, is important, because the cross product A cross B is not commutative. A cross B is not equal to B cross A. Instead, is equal to negative B cross A. So it is important to place on the second row of this matrix the first vector that is coming up in the cross product. The result of the determinant is again another vector with I, j, and k components. The j component has a minus, so sometimes as a reminder I place also the minus right there in the matrix 3 by 3. How do I find out the coefficient of the I unit vector? I cross out the first column and the first row, and I'm left with a 2 by 2 matrix. Now, AY times BZ is the first step to find the determinant of this matrix, and then I do minus AZ times BX. The next coefficient of the j vector is obtained by cancelling in your mind the second column, the one with the j. And the 2 by 2 matrix gives me AXBZ minus AZBX. The last coefficient of the k unit vector is AXBY minus AYBX. Now, this was how to find the component of the vector C. But if I just want to look at the picture and I want to figure it out which one is the direction of the vector C, you want to know that the vector C is normal to the plane that contains A and B. C is perpendicular to A and also to B. So in principle, C may be a vector pointing upward in my picture or a vector pointing downward in the picture. Of course, only one of the two directions is the correct one. Let's see how to figure it out, which one is the correct direction. Starting from the unit vector I, j, and k, you can imagine them in this trio of the coordinate of the axis. And if I do I cross j, I obtain a k. J cross k, I obtain I, and k cross I obtain j, using simply the definition of cross product. The magnitude of the first vector times the magnitude of the second times the sine of the angle in between. But there is another method that is handy when you have a picture of two random vectors, and this is called the right-hand rule. I have here in this slide two examples, one for mechanics, the torque vector, and one for electromagnetism, the magnetic force vector. On the left side of the picture, the torque vector is obtained by multiplying in cross product the r at distance times an applied force F. And if you see in the picture, you have here your hand that is closing around with the four fingers. So imagine to start by pointing your hand in the direction of the r vector, the first vector of the cross product, and then curl the fingers in the direction of the second vector, the force in this example. The thumb left alone, sticking out from your hand, will be pointing in the direction of the torque. Let's look at the picture on the right side. I have a charge that is positive, and the charge is moving with a velocity pointing to the left in the screen. This charge is moving inside a region when there is a magnetic field B that is pointing along this direction of the vector B. If you point your fingers along the V vector and then you close them, you curl them around toward the direction of the B vector, the thumb will be pointing along the F force direction. Let's see another example of right-hand rule. In this picture, on the left side, I have the same idea of curling and closing your fingers around the thumb, like if you want to hold some pencil with your four fingers. But on the right side, I have an alternative method to find the direction of the result of the cross product. Place your hand with the thumb and the four fingers separated like you see here on the screen. And the thumb now place it along the direction of the first vector of your cross product, in this example, the vector velocity. Place the four fingers of your right hand, along the direction of the magnetic field, which is the second vector in the cross product. The palm of your hand facing you in the picture here on the slide will give you the direction of the force. In this example, the force is coming out of the page. So in summary, the thumb is along the first vector of the cross product. The four fingers open are along the direction of the second vector of the cross product, and the palm is pointing toward the direction of the result of this multiplication of this vector product. Let's see an example with numbers. I have the vector A, 3i plus 2j, and the vector B, I minus 4j plus 5k, and I want to find the cross product I cross B. That is the vector C. I build a matrix with I, j, k on the first row, the coefficient 3, 2, 0 on the second row, and on the last row the 1, minus 4, and 5 for the vector B. Then I cancel in my mind the first row and the first column, and I calculate the determinant of the 2 by 2 matrix. That will give me 10i. For the next part, I cancel in my mind the second column, so that I obtain negative 15j. And for the k component, I cancel the k column, and I have 3 times negative 4, which is negative 12, minus 2 times 1, and overall that is negative 14k. Let's see now an example with a picture. I have a charged particle. The particle is positive and it has a direction of its velocity toward the right in the picture. Now place in this region a magnetic field that is pointing into the page. This symbol, this, let's say, multiplication symbol, indicate that my vector field B is all into the page, away from you looking at the screen. So now place your thumb on the direction of the velocity vector V. Place the rest of your fingers of your right hand along the direction into the page, away from you, entering the page of the screen. And the palm will give you the direction upward of the force in your picture here. So the thumb is the velocity, the four fingers of your hand, right hand, are the magnetic field B, and the palm gives you the direction of the force. Going back to the very first question, whether the vector C cross A of A cross B product was pointing upward or downward, you will see that this vector is pointing upward. You have the thumb, that is the vector A, the four fingers, the vector B, and the palm that is pointing upward. Or you can even imagine that the vector A are all your four fingers that are closing, are curling in the direction of the vector B, and the thumb will sticking up, and this is the direction of the force.